So we're here today to talk a little bit about OrangeFS. I have two of the developers here, Eliza Sorber and Walter Ligon. What's OrangeFS?
So if you go into a little bit of history, we go back to 1993, and I got a NASA grant to study parallel IO, but at the time there weren't any parallel file systems to generate patterns of data which is what we were trying to study, patterns of data from different applications. So we wrote our own, and that's what the one we call version 0. That actually turned out to be a big hit. We published papers about it. People thought it was great. And I got a couple of new PhD students, and we completely rewrote it into what was known then as PVFS, Parallel Virtual File System. And that went on almost until 2000. And at 2000, I wrote a new proposal to NASA and said, I want to write one that's not just a research toy, but is real life usable. And that's where PVFS2 started. And so I had several PhD students and master's students, and then some of them left Clemson and went to Argonne National Labs. We actually had a whole team at Argonne and a team here. And then there was a small team that started up in Ohio State. And over about 5 years, we built PVFS2 and then released it as a sort of as an open source product. And it was along about in there, I guess it was getting closer to 2008 when I met Boyd. Maybe it was 2006 or something like that. I met Boyd, and he had Omnibond, and he was like, look, I understand it's open source. We're not going to try and sell it. And I said, but what can we make it do to help promote it? And I said, a lot of people come to me and say that they can't get a service contract on PVFS. So I said, if we could offer service contracts, then maybe people would get it and buy the service contract. So that seemed like a great idea. The other thing, of course, that was happening about that time is that several other teams started working on similar products, Luster, GPS, and some things like this. They were all a little different. They had different focuses, but all the people that did that, we were all part of a community that met several times a year to share research results. And so we all shared what we were doing and mixed and matched and did things like this. And it was a pretty good thing. At that point, Boyd started focusing more on Cloudy Cluster. He started focusing more on Cloudy Cluster. He said, really what he wanted was for OrangeFS to be a tool that could be part of Cloudy Cluster that people could install just very easily the way they did in Cloudy Cluster. And so they started working on that, and it started going under that umbrella. And then it was somewhere in there, I don't remember exactly where, that we got this idea to do a version 3. And we could talk technically about how version 3 was different from version 2. It's not a brand new source base, a heavy modification of what was there. We changed some of the core technologies and then had to make everything else work with that. And it was about in that time frame also that we decided to change its name to OrangeFS, with the blessing of most of the other people who had been involved with it, because a lot of them were government employees and they have their own issues. But if you look at the code, it still says PVFS everywhere, okay? But the name of it on the outside is what we call OrangeFS. So we started doing that, and that worked really great for a number of years. We had several people in the Clemson computer department, including my wife and Mike and several other people who were working with us on OrangeFS. And the university was using OrangeFS. They were running version 2, and that was part of the whole idea, was we were supporting it. So they had their own built-in support team right here, but we were also pulling some of that to develop this next generation. And where we are today, of course, is that Eliza and I and Mike are working on different pieces of it. We could probably use 2 or 3 more people to really get stuff going, but we're working on it, making headway, and that's the good thing. And particularly me, I finally retired from the university. So I'm an emeritus faculty, so I'm with the university, but all my effort now goes into this. And it's a lot easier for me to make progress and to have more continuity than if I suddenly have to stop and write midterms and then grade midterms. And 3 weeks goes by and Eliza had to take the midterms. This was this whole thing. But now it's better because Eliza's working with us full time and I'm working sort of part time. It's the only thing I'm doing. That's the main thing. It's the only thing I'm doing is sitting here working on this. So that's really the history of how we got to where we are today.
You hinted, Eliza, how did you go from sitting in Walt's class, Professor Ligon's class, taking his midterm, and then all of a sudden you're working intently on this project with him?
I was a summer intern for Omnibond before I took Dr. Ligon's class, which I think that my summer work was pretty good training for the class, especially with certain like state machine elements. I really enjoyed that class. I think that what I'm doing part-time was a little bit hard because I always felt like I would get into it and then school would happen. And I'm like, I've completely lost my footing. I've forgotten what I'm doing. So I think in the 6-7 months that I've been full-time, I've made a lot of progress in wrapping my head around the code base and understanding how the different pieces work together.
This is a very complicated piece of code. In the past, we basically found that bringing someone fairly junior up to speed could easily take 1.5 years. Really, Eliza's done really well. She's come up faster than that. But again, she had her last year in school to get through, and that's always pretty busy.
I want to get into a little bit more of the technical side. I've heard of many distributed file systems, Lustre, of course, BZFS, and so on. What are the key features of OrangeFS that kind of make it suitable for HPC environments?
So OrangeFS is a parallel file system, which basically means that it supports taking a single file, not a set of files, but a single file, and distributing it across IO nodes so that you can read or write the contents of that file in parallel. And then also having parallel clients accessing. In other words, if you just have one program that's trying to read all this, there's only so much it's going to be able to do anyway. But when you have many of them and they're accessing this, that's the idea, is to parallelize both sides of the thing. So what we have is a program that we call the server, and it runs on a node where we're storing data. So you can't just bring a server up or take a server down. It's got to have this data persistence behind it. So usually in most of the larger configurations I've seen, people dedicate machines to this purpose. They build IO servers, they put the more advanced disks and things like that in it, and then that's where the storage is. The other thing we have is what we call the client library. It's not a complete program. It's just a library of calls: read, write, open, close, make dir, remove dir, things like that. All the standard library functions that you get in Unix, basically. And so that will run on what we call client nodes, which are nodes where you run a user's program that wants to access the file system. There's a third piece that Mike is the master of. It's what we call the kernel interface. What this is a kernel module, a Unix kernel module, which basically means it's a chunk of code that you can dynamically insert into the kernel to run. And basically what this module does is it sits next to the existing file system code, what's called the FS, the virtual file system, so that when your programmer does an open, close, read, write, and all that sort of stuff, if it's one of our files, it goes to our code, and if it's one of somebody else's files, it goes to the other code. That's built-in capability of the kernel. That's not something we wrote. All we did is wrote this little piece to put in there, and it's really pretty small, but all it does is allows you to direct requests that get sent back out of the kernel and over to our server, so that everything happens magically, if you will. You can just write a regular program. You can create a regular directory. You may not get super performance if you just make a directory and ls it, because there's just not that much stuff going on. But if you create a 100 megabyte file and then you launch 20 tasks that are going to go out and read different parts of that file all simultaneously, that it can do, and it just picks up and does it automatically. So it's very effective. So that's basically what the software does. And then we basically have those three parts. Now we have a lot of other little parts. We have little tools we've written to do things. We have utility programs that we can look at the file system and stuff like that. But most of that's not really what the user sees. In fact, most of the time, what the user sees is just the regular file system because it goes through the kernel.
If that systems administrator has to make that decision between whether they're going to go with OrangeFS versus Lustre or any of the other varieties, why would they choose OrangeFS?
You mentioned FS was actually built off of our designs. They took our designs and re-implemented the system to do that. And it's a really good product. My wife has worked with it a lot. She still works for the university in storage. So that's a good tool. Lustre was very similar to what we did, but we took a very different approach to doing it. Lustre implemented the server in the kernel and implemented most of the interface stuff in the kernel. Okay. Now, they argue that they could get better efficiency that way. Maybe they get better performance, although I don't know in the long run if you really looked over time whether they were that much faster than us or we were about the same. I think we were closer to the same. It just depended on when we released a test and they released a test. The difference is with us is our code is entirely user level. Our server runs at the user level. So in other words, you don't even have to actually be root to start it. I normally sit here when I'm developing and start 3 or 4 servers on my machine just as me, and then run programs that go out and do stuff and then come back and then see what happened and where it broke and all that kind of stuff. So that's really one of the big parts. And the difference of that is that our code was always really easy to install. It was very easy to install. And one of the big things that people ran into with Lustre, in fact, the reason that Clemson University dropped Lustre and went to us all those years ago was because Lustre had to have certain kernels. Well, a lot of these shops already have demands on their kernel from something else. And so you're trying to find a kernel that'll work with both and all of this sort of thing. So Lustre, of course, was supported by the Department of Energy. They did really well and they became really popular. We were not as popular, but then again, there are a lot of people who used it, particularly in the research domain. There's an awful lot of universities all over the world that liked working with ours. Another thing that was really interesting that we actually designed into the system was we designed the system so you can change it. Everything is made of these little pieces that fit together, these things we call state machines and these other little bits and pieces that fit in these tables and stuff. There's a lot of them. It's complicated, yes, but there are a large number of computer science PhD students took our code, implemented a new idea, ran it, and got their dissertation done. Okay, so it's been very popular for that. I think in the environment for Cloudy Cluster and Eureka, that ease of install and not being tied to a particular kernel is a big deal. Now, of course, we do have the kernel module, but that module is small and simple. It goes into just about anything. It really does. Mike keeps up with it. He's actually part of tied in with the kernel team. He actually communicates with Linus and some of those guys. And he keeps up and is constantly, as the different things change, keeps that code where it should be. And we're the only file system that did that actually got our code. Our module is distributed with the Linux kernel. They have it, not us. It's not in our repository, it's in theirs. Okay. They assumed it and took it on, and then it's maintained. And other people look at it and say, Mike, you need to change this because of something. And he's all tied into that community. Nobody else was able to do that. Lustre tried for years. They couldn't do it. I think the guys that did Lustre did an outstanding job. I mostly let my PhD student, Rob Ross, take care of that. And I tried to always stay very neutral on the subject because that's just the way I am about it. To me, the whole point of this is to provide tools that can help people do their computing. And Luster was definitely needed to make a profit eventually. And that's something that I never had to worry about.
Luster is huge in the HPC world, but there's also GPFS.
Yes.
So then how does GPFS differ? Because that's one of the other big players.
GPFS is a very different sort of animal, actually. It's completely server centric. They put almost all their code onto the server, whereas we have relatively intelligent clients. Relatively. We try not to go too far with that. Also, they're not so much into breaking up files as in taking different files and putting them in different places. So that's a little different animal than what we do. Definitely, if we wanted to, we could probably mimic that behavior. One of the things, again, because of the way we designed our code, we could do a lot of things. We've had people come up before and go, we want to try and do this. And well, you can already do that. You just know how to configure it correctly. But again, that's because we tried to make it so that it could be done like that people could come in and try out new ideas and optimize things and all that, and not be a closed system.
Eliza, though. So relatively new to Omnibond, and now you've been to this supercomputing conference and things like that. And people ask you what you do. How do you describe to the person that's in HPC, that is the systems administrator, what you do, and then how yours would fit into their ecosystem?
I think my version is probably a little bit lighter on technical details. I give just the broad overview. I explain the parallelization of it. And then if they want to know specifically what I'm working on, I explain the development process that we're doing for version 3. For example, like right now, I'm working on IO stuff, and it's a very large code base. But as far as specifics, I'm like the state machines that I've worked on and the pieces of the code that I've worked on, I understand fairly well. So I can talk about, like right now, I'm working on reading and writing 2 files. And so I could talk about something like that. But as far as parallel file systems, again, there's a few of them. Most people have seen them and encountered them before. One thing that surprised me at supercomputing was there were a handful of people who already knew what GFS, and so that was convenient because I didn't have to explain it then.
So in that case where you're talking about reading and writing, which area do you focus on? Or are you looking more into the bottlenecks that go along with it?
Whichever bug is like the most ruining our lives is usually the one that I go after and try to figure it out. And so like I was working on remove for a while. We were having errors with remove. And so I switched over to the IO side. But there's a lot of things that could be broken right now. And most of these bugs were changed for version 3, and there's pieces of the code that weren't updated correctly. My job is mostly going in and trying to find loose ends. The one that me and Walt have been emailing about for the last few weeks there was a attribute mask that I'm not sure if not being set properly is the right term. There's a check on that mask. They're checking to see if the mask has the right bits toggled before it looks like those bits were supposed to be edited. So we're still working on fixing that one. Finding the problem is, of course, usually the relatively easy part.
The file system actually operates on objects. And there's a collection of objects that make up a file. All objects have attributes, just a list of these things that are important. And then when we first designed it, we allowed for the idea that you could read or write attributes 1 or 2 at a time by setting this mask that had a bit for each attribute. That turned out to be just a total pain in the butt. And we've largely undone that with some exceptions that we won't get into right here. But still, we have this legacy, this attribute mask that is still important for certain things. And if it gets trashed, and that's what her situation was, is the mask was getting trashed. There was a sort of event. So we worked with it. I explained things, and then she went off and said, oh, okay, figure stuff out. But that's an example. And I've had similar sorts of things I've been working on pieces of code where the person who is writing the code is coming along, assuming that the thing we're working on is a particular type of object, and then jumps to another piece of code and starts assuming it's a different kind of object. And when they do that, they start overwriting variables, okay, in such a way that now later you go down and you try to look at this mask and it's trash. Okay. That's the kind of thing we're dealing with, a lot of that kind of stuff, because there's a lot of those sorts of things in there. And again, this was a very complicated change, and we had some good people, but they were only so far, they were in the middle of doing stuff when they got called back to the university. And so we are having to pick up in the middle of that. Once we get that done, though, we will eventually get to the point where we're tuning and getting stuff where it should be. But most of the basic features, like you talked about distributing data and all, that's already there. We don't have to do that. That's internal code that happens. What we're dealing with is stuff that deals with, okay, here's the biggest change we made in version 3. Here's the big secret, the big kahuna. As I said, everything we deal with is objects, and every object has a handle, and the handle was 64 bits. And it was a fixed, each server had a fixed range of handles that it could work with, which was pretty big. But there were a lot of issues with doing it that way that we could get into, but I'm going to skip over here for brevity. Primarily the issue being that you had to go to the server that owned that range in order to allocate a handle in that range. We decided to go to a new setup where we can allocate a handle where I can just pull a handle out of the air and it will go on any server. And part of that was to have a regular handle for an object like we do now, but a second handle that identified the server. And the big benefit is now you can pair that one object handle with 2 or 3 server handles, and you've got replication of metadata or data. So we went in and changed what those handles look like pretty dramatically. That's screwed up a lot of code. Most of that's actually been taken care of now. Most of that is okay. We're now dealing with some of the aftermath of some of these processes. Some of the ways that when we did that, we were able to change the flow of certain processes to be more efficient. And so that ended up rewriting this piece of code or rewriting that piece of code. And that's an example, though, of the kind of stuff that we're dealing with.
So to me, a handle is basically metadata for where the actual object is located.
Yes.
So that means by you now being able to generate these handles, like you said, out of air.
Yeah.
That means that not only can you apply needed tagging information or metadata information, but you should theoretically be able to add additional tags. So say, for instance, someone has a multiple, because you have replication now, that means that you can add different locations. So that means that inside of a handle, you can add particular information of where a data set may exist.
Exactly.
Be faster for a particular job. And so in our case, of course, we're dealing with a cloudy cluster as our metascheduler. That metascheduler can then read that and basically set a job in a location that's local to that data set, making that particular job faster.
I want to see Eureka tied in with that aspect of the file system for exactly that reason, so that when you are scheduling a job, you can say, where do I want to put my pieces of my file? Out here. Okay. Most of the things we did before, we never had more than maybe 16 servers, so it didn't make a lot of sense. But what we're going towards these days in high performance computing are these huge systems, and we need to have more flexibility like that. We need to be able to have 2 people who are running different jobs using different sets of servers, which we never did before. That was usually the worst case, is we had 15 people hitting the same servers all randomly. That made it hard, but we're trying to make it so that you can control that. And what I've tried to do is move the control for that issue off into a separate place where we can write policies and decide how do we want to do it on this system. Different systems may have different choices. So we're going to pick every other node, every other storage server, or we're going to randomly pick 5 storage servers. These are all possible things you could do. and we've done them all. But that's the idea, is to be able to go in and pick those things. And it's exactly what you were saying was exactly right. That fits perfect.
With this new level of control that some of the other file systems, of course, don't have, how are you planning on implementing the features and tools to empower the user to be able to use those different functions, as opposed to being buried down in the documentation?
There is a certain amount of that. There are some features we implemented on version 2 that I don't think ever got used because they were buried down in the documentation. And usually when I explained them to somebody, they went, "Really? You could do that?" And I was like, "Yeah, you really can." So that's a good question, is how do you get this information? I could imagine even having an AI that's, you're saying, okay, this is what we're doing. We're talking about people that are setting up big jobs. Now, we're not just going to run, it's going to run for 5 minutes. We're talking about these guys at the labs that'll run a job that runs for months.
Mhm.
Okay. They want to do things a certain way. It's worth time to sit down and think about it. Your average guy on the computer doesn't care. He just wants to throw it into the file system. And we do that fine, but we can also go in and change things. And so to do that, we have a whole nother interface. There's the standard access interface. There's something we call the management interface that allows you to go in and look at, and all these attributes and things are stored down in a database so that you can actually pull a lot of that out if you need to. And that was a big part of the early design that we haven't gotten to, that we're trying to get the core working, and then worry about is this idea of how do I write a policy that says I want to look at certain attributes and use that to make certain decisions. And I played with some ideas back in the day when we had everybody around. But right now, I think we're going to have to wait and see where we get, because I have a feeling that what we'll do is, instead of trying to do that ourselves, we'll try to use whatever we're using for a scheduler in Cloudy Cluster or what have you.
What is your absolute, and you can't duplicate each other, favorite feature of the new revision of OrangeFS? And I'll start with Walt.
My favorite feature is that it has something in it that Eliza doesn't even know about, called the SID cache, which is SIDs are what we call those handles that tell you where something's located, and you can have multiple ones. Okay, so we have essentially a database of those things, and the ability to search through that and make policy decisions about, like we said, locating data or optimizing flow, that sort of stuff. I think that's where the real beauty is going to come. And there's pieces of that in there. There's a lot of it there. We call it, but I just have a fixed policy that just gives you the server 1, 2, 3. That's all it does. So that's my favorite piece.
I'm gonna go basic, but I think that the most exciting thing is just this potential and possibility for replication. I think that's gonna strengthen it a lot.
I'm assuming parts of it are still considered open source.
It's entirely open source.
It's parallel. So in that case, if you had the entire OrangeFS community listening right now, what would you ask them to do?
The actual truth to that question is not very satisfying. I'd be afraid to ask the community right now. I'd ask them, what features do you think you want? And I'd describe some of these ideas and see if any of them hit. But I'd be prepared for the idea that they have to go away and think about it for a month and then come back and go, well, that would be pretty good. But it's very hard to do. Most of my career is trying to get to understand what people might want. Otherwise, how do I know?
Eliza, as a unjaded, fresh-faced, positive, excited to be here developer with thousands of foaming at the mouth or OrangeFS users looking to you for guidance, what do you want to hold your flag up and say as a call to action for this great, huge community of OrangeFS users?
It's such a cool code base. And I think these thousands of foaming at the mouth OrangeFS users definitely agree with that. I would tell them that version 3 is going to be super cool when it's going to come out. And I think it's going to be really exciting once version 3 gets into like the end stages and everything starts working really well.